So good morning, everyone, and welcome to the conclusive session of the second edition of Fair February. Today, we are having actually a very exciting speaker lineup around the theme of social justice and design. So before starting with our first guest, let me share with you how the session will work. So speakers will have their talk, and throughout the presentation, the audience can drop questions in the chat. And at the end of the talk, there are gonna be 5-10 minutes for questions. So I think we can start now introducing our first guest, Jessica Joan Finocchiaro, whose talk will be about bridging mechanism design and machine learning toward algorithmic fairness. So Jessie is a fifth-year PhD student at the University of Colorado Boulder, working with Dr. Rafael Frongilio, and she's an NSF Graduate Research Fellow. Her research focuses on design of proper scoring rules for general prediction tasks, as well as understanding how the choice of scoring rule affects algorithm decision-making and recommendation. She holds a master in computer science for CU Boulder and a bachelor in mathematics and computer science from Florida Southern College. So Jessie, I think I leave the floor to you.
Thank you everyone for being here and joining this morning, I guess, first of all. And thank you for the introduction. Like Christina said, I'm going to talk about some work that was published at FACT, or the Conference on Fairness, Accountability, and Transparency in 2021. And this is joint work with a team of machine learning researchers, social networks, and data science researchers, as well as economists. And so the full list of collaborators is Roland Mao, Pedro Manahu, Rob Patro, Manish Raghavan, Anna Stoicha, and Stratis Surtis. And kind of one of the cool things about this is that I have only met two of these collaborators in person. So hooray for Zoom era collaboration. And part of the reason for that is we have folks in a couple of different continents on this team. So I guess kind of to tee up how this paper thinks about modeling social systems, we can think about the fact that algorithmic decision-making is on the rise. And as like one, personally, I think kind of like creepy example is I currently live with my sister-in-law and brother and their two children who are both currently in diapers. And even though I don't have any children of my own, I now get Snapchat ads for the exact brand of diaper and the exact size that my younger nephew wears. And part of this is just because of how we're leveraging data to make decisions on like who wants to show me an advertisement. And then algorithms are also being used to kind of fit parameters for pretrial risk assessment indicators to decide whether or not to release somebody on bail before their trial, deeming them as high risk or not. It's used to not only determine or estimate housing prices like Zillow estimates, but also used to determine who to actually give a loan to. This is a couple from Florida who their story kind of went viral when essentially they got an appraisal on their house and they thought that it was kind of undervalued, and they ended up taking down photos of the wife's family who are all primarily Black, and getting another appraisal, the value of their house increased. We also have examples like ride sharing, where Uber not only has to decide how to match potential drivers to customers, but also uses machine learning maybe to calculate shortest path in current traffic conditions, things like this. And this is actually an example from the Boston Public Schools website where the city collaborated with economists to come up with some sort of matching mechanism to match students to schools. And there's kind of a storied history in that that's pretty fun. And so this talk will kind of primarily talk about machine learning and mechanism design as two tools to think about how to model these systems. But these are just two of many tools that we can study. And I also kind of maybe want to point attention to this like historic shift from like descriptive characteristics of algorithms to prescriptive. So instead of just using an algorithm to say, oh, this is an image of a cat, or, oh, this person is XYZ. Now we're saying, oh, we're making predictions about the future. Like this person is likely to recidivize. This house is worth XYZ dollars. And so kind of before we hop into everything, I'll talk briefly about the mechanism design and machine learning setups. But to give kind of an overview, game theory studies how agents interact with each other, as well as with systems in order to receive some sort of best benefit. And so you can think of, if you're playing rock, paper, scissors, maybe you model the game as like a two-person game and you get 1 if you win, you get 0 if you tie, you get -1 if you lose. And then you can kind of study how agents behave like in relationship to each other if they have some belief over someone else's distributions. And mechanism design kind of turns out on its head where we want to, often we think about allocating goods to agents so that, or maybe this is the design of the game. And so we want this so that maybe algorithm or allocations, these algorithms can be run in polynomial time. And maybe we want to incentivize these agents to be honest, meaning that like no matter what they believe other people are going to do. And so like if I think that Christina is always going to play papers, then paper in rock, paper, scissors, then I would want to always play scissors. Even if I like actually liked rock over scissors in some sense, whatever that means. But we want agents to be honest. And so we can try and design mechanisms to incentivize this. And often we want allocations that are quote unquote fair or good for the community. And so a lot of times this gets measured by being NB free, which is to say, if I have my allocation, someone else has theirs, I prefer mine over theirs. And often we want this to be Pareto optimal. So you can't change any one person's allocation without making another person's allocation worse off. And then maybe within this Pareto frontier, we want to think about different spots on the frontier. So maybe we want to maximize the minimum utility of somebody, and that is like this Rawlsian notion of fairness. Or we could look at the Nash social welfare, which takes the geometric mean. And so you can argue that this kind of reduces the variance in some sense. Or we could look at the utilitarian social welfare, which is the sums of everybody's utilities. And I think Cyrus is going to have a talk on this later, from my understanding. And then maybe we can think a little bit about the machine learning setup where predictive ML algorithms, to overgeneralize, are designed to learn some hypothesis function that maps features to predictions. And the way that we do this is we optimize some objective or a loss function. And so one example of an objective is maybe we want to maximize the probability of a correct classification. And then maybe we'll impose some constraints. So in the fairness literature, we can think about maybe we need our hypothesis to be independent of the sensitive variable. So if maybe we want something to be fair, like group fair on the basis of race, then we don't want race to actually factor into our hypothesis. And kind of similarly, maybe we want to equalize predictive parity on the positive class. So if we're trying to decide how many students get into a certain university, maybe all of the qualified students are accepted at the same rates. It's called equalized odds. And there's also maybe other constraints like plausibility constraints where we want to restrict to linear hypotheses and things like this. And now maybe with this background, we can jump into kind of the content of the paper. And so our work introduces and contrasts the approaches to understanding and mitigating fairness and discrimination by both mechanism design and machine learning. And so what we do is we enumerate 5 lessons that can be kind of translated from one field to another. And I think that we were a little bit generous where we kind of claimed some things were machine learning when really I think that they're data science or HCI lessons. But some of these lessons include designing for strategic agents, studying the long-term effects of fairness, defining and diagnosing unfairness under uncertainty, as well as resource allocation constraints and human perceptions of fairness. Again, I think that this is really a joint effort with HCI as far as a lesson. And we're going to kind of focus on these first 3 today. And then if we have time, I'll kind of add in a critique of the role that algorithms play in a broader context. And so if you're interested in the other lessons, I highly recommend the paper. Also, just kind of highly recommend the paper in general because it was really fun to write and talk to my collaborators on it. But we're going to focus on these 3 lessons. And so with that, we'll kind of jump into designing for strategic agents. So as algorithmic decision-making is increasingly incorporated into our lives, people have become more aware of its presence. We've seen people chanting, "Screw the algorithm," when at peak, or I guess early COVID, it was used to replace people's test scores. And there was lots of socioeconomic discrimination within that. And maybe one other example is there was a couple with joint finances who applied for Apple credit cards in 2019. And both the husband and wife were granted the credit card, but the husband was actually granted the card with a credit limit 20 times that of his wife. And so this kind of prompted some investigation into Goldman Sachs' algorithm because they were running this algorithm on behalf of Apple. And something kind of interesting that came out of this is that Steve Wozniak, who is high up at Apple, actually noted that he and his partner had the same disparity emerge. And so this kind of emphasizes the demand for algorithmic interpretability and intelligibility, meaning like, can we kind of query the algorithm? And even if we don't understand like the nuts and bolts of the algorithm, can we at least get some sort of sense of what's going on? And so this desire for intelligibility is particularly common in settings with homogeneous preferences or resource constraints. Meaning like if you're applying for a credit card, you probably want to actually get that credit card, or if you're applying for a university, you want to get in. And so that's kind of what I mean by homogeneous constraints. If someone's able to present themselves as a better candidate by maybe paying off outstanding debts, using a parent's address from a higher income neighborhood, or other things, they're likely to do so. And so fair algorithm design needs to kind of take this into consideration. Whoopsies. And we'll maybe kind of return to this example or to a running example considering university admissions and observe that they kind of like university admissions have these same characteristics where we have homogeneous preferences. And students might actually go above and beyond to make themselves more appealing to a university. And so to make this discussion concrete, we can consider our college applicant Taylor, and they are applying to universities, and maybe they had a rough first attempt at the SAT, but let's say that the university is using GPA, SAT, and an essay to decide whether or not to admit Taylor. And so in some sense, Taylor wants to be strategic and they want to make themselves look as appealing as possible to this university. And so the university sees their SAT, they decide it's too low and they deny it. But maybe with some sort of intelligibility or recourse, the university can give feedback to say, oh, you should increase your SAT. But of course, this can introduce disparity in outcomes because low-income students often are not able to afford to take the SAT twice, or maybe Taylor's well off enough to hire a tutor, and that's not an opportunity for a lot of students. And so this previous scenario is kind of additionally incomplete because Taylor is not the only person applying to the university. So now we can maybe suppose that Alex also applies to the university. And maybe while Taylor was not able to afford to take the SAT twice, Alex could. And she improved her score so that she looks better to the university. And obviously both Alex and Taylor are trying to be admitted, but maybe because Alex was able to take the SAT twice, only Alex is able to get above the university's admission threshold. And maybe this threshold is also determined by resource allocation constraints, like the number of beds that the university is able to house freshmen in, or the number of students that they can kind of be able to teach an expectation. And maybe as an aside, homogeneous preferences are not always to be assumed, but that's a story for another day. And so we can formalize this a bit more rigorously on what it looks like for agents to be strategic. So we can say that each player I has a set of features. Here we'll say it's just GPA and SAT. And the university will deploy some classifier F that maps each point xi to either a plus or a minus, accept or decline. And players can invest time, money, etc. to change their features. And so what kind of happens here is, let's say here's our threshold. Right now, both people are not able to, or are not getting accepted to the university. But if they have access to this classifier, what Orange will want to do is they'll basically want to move the minimum distance to attain a positive classification. And I'll say, if anyone's watching this inverted, orange is blue and purple is green. And so we can also think about decision-making under fairness constraints. And so for now, we'll focus on demographic parity, which is to say the expected treatment for somebody should be independent of their group identity. And so we'll say that this classifier attains demographic parity if members of different groups attain the positive classification at the same rates. And so here we have 4 orange and 4 purple people. And if we deploy this classifier, this attains demographic parity since the expected treatment or the probability that somebody gets accepted is 1/2 for both groups. But in general, if one group is advantaged over another, they can afford to pay the cost to change their features, while disadvantaged groups or members of disadvantaged groups often cannot. And so this imposes some inequality here. And kind of the next thing for the sake of time is diagnosing unfairness. And so what do we mean by this? There's many roles that computing can serve, one of them being diagnostic, and I would highly recommend this paper by Abebe et al. To kind of go more into some of these roles. And there's so many moving parts to a system. The machine learning fairness community kind of gives us the tools to diagnose in some sense or audit, like, is an algorithm unfair? Is this mechanism unfair? And this is even true when algorithms are treated as a black box. And so this kind of brings in this intelligibility aspect where even if the algorithm's a black box, we can still at least know what it's like, what the outcome is, even if we don't know the process along the way. But maybe one issue that comes up is that predictions are often one shot. And so there's often uncertainty in our predictions. And these metrics of diagnosis are often in contention with one another. So there's a result from Manish Raghavan and John Kleinberg and Sendil Mullainathan, where, as well as Alex Choltakova from 2017, that gives impossibility of satisfying multiple fairness metrics simultaneously. And so this fairness metric, if you're going to choose to commit to one, you have to think really carefully and kind of in collaboration with stakeholders about which one you want to aim for. And so if we go back to our university admissions example, I'm just going to give 2 examples of maybe we implement the same classifier, but different population distributions that people are drawn from. And if we look at the example on the right, we can see that the orange people are accepted at way higher rates than the purple people, as opposed to on the left, this is maybe a bit more equalized. And this kind of fairness notion of, oh, well, we committed to demographic parity and we see that we're satisfying demographic parity on the left, but we're not satisfying it on the right, kind of gives us this vocabulary to diagnose unfairness. And kind of for our whirlwind tour, the last major lesson that we'll dive into is the long-term effects of fairness. And so deploying an algorithm to make decisions about people impacts these people. And machine learning and mechanism design researchers have both kind of designed tools to think about feedback loops that are generated by these algorithmic decision-making systems, kind of in three main classes. The first is if we're thinking about two-stage models, so just we deploy this classifier at time step 1, people react, what does it look like at time step 2? In reinforcement learning settings, we can think about what it means to be fair in the infinite time horizon, or in equilibrium, and this is kind of the common like economics mechanism design tool. And there's an increasing push for studying algorithmic recourse. I know that Suresh is faculty at Brown, and I know that he's been one of the pioneering researchers on this. So hopefully some of you guys here are familiar with that work. And to kind of think about, even just in the two-stage example, let's consider this classifier that's trained on this group of applicants, and maybe the applicants are strategic, but multiple people study long-term effects of fairness. Sorry, I looked at the wrong place in my notes. So let's say that we admit students in our disadvantaged group at the same rates as students in our advantaged group, but then maybe the university doesn't actually put structure in place to support disadvantaged students once they actually enroll. These students might drop out or withdraw from the university at higher rates, go home, tell their friends about their negative experiences, and then their friends are now uninclined to apply to this or maybe any university. And this is something that, like, in conversations with our department chair at CU is very common in our undergraduate population. And so this now actually affects and changes the underlying distribution of students applying to the university. And so now maybe in year 2, this is what our application group looks like. But if we continuously deploy this group VAR classifier, maybe we accept this purple student, but without any institutional support for them, maybe we're actually setting them up for failure to no fault of their own. And so to kind of start to wrap up, we can think about why these considerations matter. And all of this is kind of moving into our critique of algorithmic systems and studying them on their own. And so we need to contextualize within larger systems. And our primary critique is just algorithm design is only one part of the algorithmic ecosystem. And so in some sense, it's often insufficient to model fairness solely through these algorithms. And so this is maybe an oversimplified chart of like an algorithmic ecosystem that we'll talk about, where we start off in this top left-ish corner of problem identification and development. We go to stakeholders, collect data, clean and debias that data in some sense, actually develop an algorithm, deploy it, and maybe as we're going through, we can imagine this is closer to like a fully connected graph, where maybe after we clean the data, we realize like, oh, this isn't actually the data we need. We go back to stakeholders, things like this. Maybe we collect more data after. And so maybe I kind of have like one spotlight per thing, but Abeba Berhane talks about this in her recent paper as far as just like the issue of problem identification and development. And she contends that mathematical models are too close to Cartesian and Newtonian worldviews in aiming to classify and sort the world into buckets, but that these models often are not suited to make predictions about human behavior in social context. And these, in doing so, maybe like deploying an algorithm in the wrong setting can present real harms, particularly to the most marginalized by society. And then once a problem's identified, stakeholders in the proposed solution need to be consulted. So these stakeholders include those purchasing a piece of the software or the algorithm, developers, consumers, and maybe those on whom the algorithm will be deployed. And maybe those are all different people. If you think about algorithms used in elementary schools, maybe algorithms are deployed on students but used by teachers. And so one example of this is Sasha Kostenchak in her book Design Justice discusses her experience as a trans woman going through airport security. And as someone going through the screening, as someone goes through the screening machine, a security agent's forced to assume and impose some binary gender on the person going through security. But if and when the person's body scan doesn't match the algorithm's perception of what a male or female should be, they're potentially outed, subject to more invasive screening, or flagged as potential threats. And maybe had a trans user been consulted or prototyped in this stage of the algorithmic ecosystem, maybe this could have been avoided. And for the sake of time, I'll maybe breeze through the rest of these, but you can think about issues that come up with gender shades, where Joy Buolamwini and Tim Nickabrew just audit computer vision APIs to show very disparate performance on folks of darker skin tones. If anyone's familiar with Microsoft Tay, there was a bunch of racist kind of behavior that was taught to this algorithm, in part because it was learned in real time. There's no way to debias this data. And we talked about algorithm development and testing. And so, again, this is kind of two of many fields that we could think about. I think that we still have a ton of lessons to learn from sociology, political philosophy, human-computer interaction, AI ethics, as well as practice-driven work from nonprofits, from policymakers, community organizers and activists, as well as investigative journalism. And so kind of in summary, I am sorry I gave you no solutions. I mostly just said that designing equitable algorithmic systems is hard, but it is easy to perpetuate historical and systemic biases. How to ensure algorithms are fair is contested, and so we have kind of these clashing notions. And machine learning and mechanism design are two ways of many to think about modeling these systems. But they have kind of in the past, I would say like 5 to 10 years, learned a lot of lessons from each other. But I think that there are still lots of lessons to learn, and practical issues arise in these models, such as coping with strategic agents, thinking about trade-offs between quantitative fairness, welfare, inequality, and optimality, which we didn't really talk about today, and remembering that algorithms operate within a larger ecosystem. And so with that, I will kind of conclude here and take any questions.
Thank you, Jessie, for the interesting talk. And are there any questions in the audience? Otherwise, I actually have one. So my question is, it's more a curiosity likely. So I wanted to ask you, Jessie, if right now there is there is a lot of research and studies around this topic, and I was just wondering whether some of the solutions that have been proposed are actually applied somewhere. So are there specific environments, like I hear often about university admissions. I know maybe about standard policies of affirmative actions. Instead, these are maybe what you presented. It's kind of more statistically oriented. So there should be the usage of models. So do you know to what extent these new algorithmic fairness constrained algorithms are employed in practice, or if we are on the right path to make them applicable somehow?
Yeah, that's a great question. I can give, I guess, the example of university admissions. If I'm remembering correctly, I know Clemson University and University of Texas at Austin were both using algorithms to kind of at least like pre-process their admissions. And I think for UT Austin, it was actually for a graduate program. And basically when they actually found like all of this evidence of discrimination, I know this was a big thing at UT. There's actually a push, instead of trying to fix the algorithm or just make it better, to just get rid of the algorithm altogether. And I think that's a totally acceptable solution in a lot of situations. And it just kind of depends on, I don't know, I think that we're very inclined to build first, ask questions later, and maybe we need to ask kind of some of the hard questions first. And then another example that I kind of briefly mentioned at the beginning is in Boston Public Schools. Essentially, there are two economists whose names are escaping me right now, who've worked with Boston Public Schools, New York City, Minneapolis, and Chicago, I think. And essentially, they went and worked with the schools and talked about different, essentially, what they were doing before was a individual acceptance mechanism where students would rank their top 5 schools, or immediate acceptance, sorry. They would rank their top 5 schools, and then everybody would get matched to their first school if there was room, and if there wasn't room, then they would go down the list. But now if your second choice already was filled with like people whose first choice their second choice school was, it now makes you a lot less likely to get your second or third choice. And so people were being strategic where maybe some people were being strategic where maybe school B was really their second choice, but they put it first because they thought that they were more likely to get into school B. And so these economists came in and they essentially generalized the stable marriage allocation mechanism, which is a deferred acceptance, and it kind of has this characteristic of being strategy proof. And there was still a lot of contention on whether or not that was the best thing. They also proposed top trading cycles, which is another mechanism I don't know that much about. And so I guess long answer short, these are getting used at times, but I also think that there's a lot of abstractions that often get made in order to use them.
Thank you. So just little follow-up question, but maybe there is no answer yet. So far, for what concern the study of the long-term effect, everything is just at model level or, I mean, synthetic experiments, and there are no maybe actual environments in which they have been realistically tested the effect of fairness policy.
At least the main papers that I'm thinking of, most of their results were like theoretical supplemented by synthetic experiments. But some of the work from like Brian Wilder, he's more of a, I wouldn't say network scientist, but he does some great work on just how do we stage interventions on social networks in order to think about the spread of information. And they've done field studies where they look at essentially how do we educate some subset of the homeless youth population in LA in order to like actually reduce the number of cases of HIV and HIV transmission in this community. And so I know that they've done field studies and that's kind of long-term effects, but as far as maybe some of the fairness long-term effects papers, I'm not too sure.
Thank you, Jessie. Thank you. So I think that we are a bit late, but we should start to introduce our second